Okay, so question is to study the following polypeptide chain written below. A, draw the structure of the polypeptide as it would appear if placed in a solution whose pH is 1. Show the structure and calculate its net charge at pH 12. And finally, define the isoelectric point of an amino acid. State its importance in protein chemistry. So first, let's look at the polypeptide chain that we have. And this is the 3-letter symbols for all of these amino acids. And let's just define what each of these amino acids are. So when we have TYR, this is the tyrosine amino acid. Gly is glycine. That Liz is lysine. And finally, the glue is glutamic acid. I'm gonna run out of space, so let me just move that over. Glutamic acid. Okay, so now that I have defined what each of these are, I'm first going to draw out all of the different amino acids bonded together, and then I'm just going to label what all of their pKa values are, or I try to answer the question. So every amino acid has an amine group, and what makes each of these acids unique is that they have a different R group. So first I'll draw the R group for tyrosine. So tyrosine has this phenyl ring and also an alcohol group attached to it as well. And then I'll just draw the rest of the amino acid. So I'll draw its carboxylic acid functionality. And then I'll just start to draw the next amino acid, which is glycine. So here is glycine's amino group. And glycine is one of the more simpler amino acids, so its R group is only a hydrogen. And then this is its carboxyl functionality. And now we'll start to draw lysine. So this is the amino group on lysine. And now if we were to draw its R group, I'm just going to draw its chain. I think it has a 4-carbon chain. With an amine group at the end. And then I'll draw the carboxylic functionality of the lysine. And then finally, we'll draw glutamic acid. So this is its amine group, its carbon, and then it has a 3-carbon chain. And the reason why it's glutamic acid is because it contains a carboxylic acid at the end, like so. And I'll also draw out the end of the polypeptide chain, which is its carboxylic acid group, like that. Okay, so now that we have the structure written out, we're going to look up the different pKa values of these amino acids. Okay, so here's a nice chart that summarizes all the different pKa values of these different amino acids. And notice that they have it for all of their carboxy groups, all of their amino groups, and also for all of the side chains. So let's look at tyrosine first. So its pKa group for the amino is 9.11. So let me just highlight this in green and then show that its pKa is 9.11. And we don't have to worry about its alpha carboxy group because it is part of the chain, so it doesn't have a hydrogen there. But we also want to look at its side chain. So the side chain, which is the alcohol group on the phenyl ring, has a pKa of 10.07. I'm also going to circle this and say the pKa is 10.07. Okay, so now that was all of the tyrosine. So notice that for glycine, you can't deprotonate its side chain, so we don't need to write anything down for glycine. And now let's look at lysine. So it's found here under the basic amino acids, and I'll highlight this in red. And we just need to look at lysine's side chain pKa, which is 10.79. So let me just highlight this, and its pKa is 10.79. And finally, let's look at glutamic acid. So I'll underline this in orange. And then on the chart, it's found here under acidic amino acids. So for its side chain, it has a pKa of 4.25. And for its alpha carboxy group, its pKa value is 2.19. So this is the hydrogen on here. Its pKa is 2.19. Okay, so now we know all the pKa's of all of these different structures, and we can finally try to answer our question. So the first part is to draw the structure as it would appear if placed in a solution whose pH is 1. So that's a very low pH value. And I'll just write down here that when your pH is less than your pKa value, then this tells us that the groups are protonated. So every time we have our alcohol groups, that just means that they'll have their hydrogen on. And when we have our amine groups, that means that they'll have an extra hydrogen bonded to the group. So now let's try to draw out what this chain would look like. So notice that all of these pKa values are greater than the pH equal to 1. So they're all going to be protonated. So the amine group on our tyrosine will have an extra hydrogen. So this will be protonated. And then I'm just going to draw the rest of my chain. So bear with me because it's a long chain. And in the case of our alcohol group, this just means that it has the hydrogen on. So I'm not going to add an extra hydrogen onto there. And then we'll just continue on with the rest of our chain. So glycine was the easiest one. It just has the hydrogen there. And then on to the next amino acid. It's going to draw this as a line structure to make it easier. And now this amino group is protonated. One, two, three. And then finally, our end group. Okay, so this is the structure when the pH is 1. So notice that our amine groups are protonated because their pKa values are greater than the pH. Okay, so now let's do the second part of our question. Show the structure and calculate its net charge at pH 12. So I'm going to start a new page. Obviously, I don't think I can fit everything there. So this is for 6b. And the pKa, or the pH, is now greater than our pKa values. So when the pH is greater than your pKa, this means that the groups are deprotonated. So now let's draw our amino acid chain. So we have our amine group, and then we have our tyrosine. And if we look at the alcohol group on our tyrosine, then it becomes deprotonated because now the pH is 12. And then let's carry on writing the rest of these. Again, our glycine just stays the same. And then moving on, we have our lysine. And it no longer has an extra hydrogen. And then finally, we'll have our glutamic acid. And its carboxylic acid group is now deprotonated. And the same thing with its alpha carboxy group, it's also deprotonated. So now let's look at all of the charges in this molecule. We have 1, 2, 3 negative charges. So therefore, the net charge is -3. Okay, so now let's read 6c. Define the isoelectric point of an amino acid. State its importance in protein chemistry. Okay, so the isoelectric point, let me write it down. This is when the charge of your amino acid or amino acid chain is neutral. So this is important in protein chemistry because it affects the reactivity and also the stability of a protein. Okay, so that was all of question 6. So let's see what the junior tutor said. The charge of the terminal amino and carboxylic groups and the R groups of the amino acids involved in the polypeptide varies depending on the pH of the solution. If the pH of the solution is less than the pKa of the group, that certain group will exist in its protonated form. Meanwhile, if the pH of the solution is greater than the pKa of the group, that certain group will exist as its basic form. Yep. So since the charge of the groups will vary, the net charge of the polypeptide also changes depending on the pH of the solution. And to compute the net charge, just add all the charges of the groups that can be protonated and deprotonated. So they show that the net charge is equal to the sum of the charge of all the groups. So here they have, in the case of tyrosine, glycine, lysine, and glutamic acid polypeptide chain, the structure of the polypeptide, including the pKa of the groups, is shown below. Okay, so it's slightly different values, but it is around the same, so 9, 10, 4, and like 2. I noticed they didn't include the one for the OH group on tyrosine, but I'll just keep that in mind down here. So now for part A is to draw the structure of the polypeptide as it would appear if placed in a solution whose pH is 1. So comparing the pH and pKa values, all the pKa are greater than the pH of the solution, therefore all of the encircled groups will be protonated. Okay, they circled all the groups. Yep, so that's correct. And then show the structure and calculate its net charge at pH 12. So pH 12 is greater than all the pKa of the encircled groups, therefore they will exist in the solution as their deprotonated or basic form. So I think everything's correct except they just forgot to include the pKa of tyrosine's side group, which is around 10, so this would also be deprotonated like I have here. And they calculated the net charge equal to -2, but it should be -3. So I'm just going to write that at the end. And then for part C, it says to define the isoelectric point of an amino acid, state its importance in protein chemistry. So the isoelectric point of an amino acid is the pH at which the charge of the amino acid is neutral. It is very important in protein chemistry since the reactivity and stability of the protein depends on its charge. Aside from that, the structure of the protein can be disrupted depending on the pH on which it is placed. Okay, so this solution, or this, I'll say explanation, and the structures are mostly correct. However, the pKa of the OH group on tyrosine, I believe. Yep. On tyrosine, around 10.07. So therefore, it will also be deprotonated when the pH of the solution is 12. This makes the net charge in part B equal to -3. But they had a really good explanation. I think they just forgot to write down the pKa of tyrosine. Yeah, so it has 10.07. Okay, so maybe they can fix that. So this solution, I'll say, is incorrect, even though it was mainly correct.